All right. Big apologies for that delay, and fun to see so many external people attending this seminar, held by our guest researcher Hanan, who can start by introducing herself.
بسم الله الرحمن الرحيم. رب اشرح لي صدري ويسر لي أمري واحلل عقدة من لساني يفقهوا قولي. I'm starting by the name of God and by welcoming you all to this quite long seminar, not very short but also not very long. I'm happy to be with you today. Actually, I'm excited to be here as a speaker, not only because we are in Max 4, which is the brightest light source in the world. That's already well known, but for me personally, because Max 4 is part of Lund University, one of the oldest and most prestigious universities in the world. And as a physicist, I'm personally involved in the history of physics. So maybe I don't need to remind you that Lund University is well known in its roots, deep connection with spectroscopy. So most of the pioneering work in spectroscopy was done in Lund. So imagine how I'm excited to speak to you on this land. And back to the presentation, my presentation titled as A Glimpse into NIPICO Spectroscopy, Insights from a Guest Researcher at FinEstBeAMS. So I'm proud to be presenting FinEstBeAMS in front of Max 4 staff. And as I was asked by Eric to introduce myself, as you can see, I'm Associate Professor of Atomic and Molecular Physics at the University of Jordan. And this work is in collaboration with my colleagues Antti, Christian, Kevin, and Richard from other synchrotrons and universities. And to introduce myself better, I would like to start with this picture, a serious picture from the graduation book of my university. It's not my best picture, but it's the best picture that my mother liked most. So that's why I'm starting with it today. And why I'm doing this for the first time in any of my presentations to show this picture, as I said, it's dear to my mother, especially in this week, in this month, in this period of time. If I have time at the end of the presentation, I will tell you why I put this today in my presentation. So, as a university professor at the University of Jordan, specialized in atomic and molecular physics, I'm not only a researcher. I'm not only doing research on accelerator-based techniques in the field of atomic and molecular physics. My life is so busy with so many nice things besides research. I'm also doing teaching, education, student mentorship, outreach activities, anything related to science, to physics, to students is related to my life. So I live busy life with all these lovely stuff, and today I'm presenting side of my life, which is research. And as you said in the big slide of the title of the presentation, I am proud to be today presenting two prestigious light sources. Please don't be jealous. I am in coincidence a collaborator in Electra light source and also at the same time in Max 4. So when Electra decided to switch off her light in the past few months, I was so lucky to find another light source to host me. So I took my luggage and I did fly to be here with you in Max 4. And back to science, let's talk science, and back to the presentation. From the title, you would see that I may divide my presentation in order not to be boring, and also in order to be informative in the way that I would like to present it into two parts. So you will find two highlights in my talk. First of all, science comes first, and glimpse into NIPICO spectroscopy, which is related to the work that I did during my visit to FinEstBeAMS, and that's to make the beamline manager, my colleague, my friend, Antti, happy. The other part, a few coincidences inside, that's for myself and to share the experience with you, and also with anyone who would attend the presentation, including my friends, my colleagues, my students, because I believe science is nothing without us human, without us scientists. So I would like to share with you also my personal perspective about coincidence measurements. Starting with the first part, the whole presentation will be about NIPICO spectroscopy. When NIPICO comes on the screen, it stands for negative ion, positive ion coincidence. Sometimes I write the word spectroscopy, sometimes I go short and I say NIPICO. So even if I say NIPICO, it means NIPICO spectroscopy or NIPICO technique. To introduce you about the motivation of NIPICO, the purpose of doing NIPICO measurement, even before telling you about the instrumentation, the obtained results, we need to highlight the purpose and the grand motivation of using synchrotron radiation for atomic and molecular physics. So the general aim of using synchrotron radiation for atomic and molecular physics is to shine some light in the vacuum ultraviolet region or the soft X-ray region and watch the electronic transition in the valence or inner orbitals, and then using this information to understand the electronic structure of material. That's what we call electron spectroscopy. But also, synchrotron radiation is useful to do ion spectroscopy, to shine light on the molecular systems and to study them particularly in isolated states, in gas state. And if we do so, we normally start with small molecules because go simpler, you go faster, you go more confident, and then when you get some knowledge, you dare to go more complicated and you start to touch more complicated systems. And in that sense, ion spectroscopy is a well-known technique to study photo-induced fragmentation. And in general, this photo-induced fragmentation in atomic and molecular physics is used by utilizing vacuum ultraviolet or soft X-ray radiation. If that happens, or if the molecule is exposed to such radiation, it would be disturbed, it would be excited. So it would be an unstable state. Eventually, at the end, it cannot stay that excited, it would decay. One of the decay products would be positive ion, negative ion, could be electron, could be anything, and one of them could be anion or negative ion. And in NIPICO, back to the terminology, negative ion, positive ion coincidence. What NIPICO adds to the conventional ion spectroscopy is this detection of negatively charged particle, and also not only detecting it, but detecting it in coincidence with the positive ion. So we are mainly concerned about negative ion formation. What are the possible paths of getting anion as a final product of photon-matter fragmentation or photon-matter interaction? There would be two possibilities, or one of the other possibilities, depending on the energy of the used radiation, or depending on the energy of the probe of the experiment, of the light used. So in the case of the valence region, it's a process called ion pair formation, where the molecule is excited by vacuum ultraviolet radiation and eventually decays into positive negative ion pair. That's the simplest case. And this happens in the valence region, and this describes the basic principle of the results that I would show today. The other possibility, if we shine the molecule with a bit higher energy, soft X-ray, then we are in the core region, and the molecule would get either core excited or maybe core ionized. But here, the negative ion is not directly produced from the core excited or core ionized ions. It eventually be the dissociation product after a process of electron emission, even in contrary to the previous process where no electrons were emitted. And the second situation where we probe the molecules using soft X-ray radiation was the technique or the energy range used in all previously published NIPICO results, all results that were done with the NIPICO setup. Back to this technique, to the motivation of NIPICO. So we understood that ion spectroscopy is a well-known technique in synchrotron light sources, especially for atomic and molecular physicists. But the interest is mainly devoted to detecting positive ions. And even if some experiments were detecting anions or negative ions, they do that without coincidence measurement. So you detect the ion, but you don't know this negative ion with what it coincides. So the role of NIPICO is to detect these ions and to give more information about the photodissociation process and about which ionic channels or which positive, negative channel would be produced in the process. And if we get that information, we would add or complement the information that is already obtained using the conventional ion spectroscopic techniques. Why NIPICO is special? Why I chose NIPICO to come to Max 4 and to work on that technique? There are many reasons. I would briefly say it's unique, it's important, it's sensitive, and above all, for me, it's tricky. Let's say why it's unique. Simply, this is the only light source that hosts NIPICO nowadays. So if you want to do NIPICO, you have to find your visa to Max 4. And if you submit a proposal using that experiment, you will be happy that the review panel will tell unique setup, unique experiment only available at FinEstBeAMS. So that's an advantage. For me, a user who submits a proposal for the first time to Max 4, according to Max 4, I'm unknown, but they know NIPICO and they know they have it. So just I need to write a logical proposal, a reasonable proposal, and it's a unique technique. It's important in the sense that, as I said in the introduction, it can give you information about ion pairs, not only the negative ion produced, but with which positive ion that negative ion coincides. And also, not only with which positive ion it coincides, but also at which photon energy it would appear. So it gives also the appearance of energy of this ion pair. It's sensitive in the sense that it enables us to detect the coincidence of multi-particle, not only positive ion, negative ion. It also could be a coincidence between a negative ion and two positive ions, three positive ions. So that is also possible through the sensitive techniques. And also, it is sensitive in the sense that you can detect anions that were not visible, not observed, not detectable using the conventional technique. And lastly, it's tricky. I would say you cannot guess what you would see in the spectrum. You always need to do your own calculation. You always need to play with the potential. You always need to sit and think, is this peak true coincidence? Is it NIPICO or it is something else? So it's not a typical spectrum that you get and you know beforehand what the results would be. Before going to the instrumentation of NIPICO, I would like to show you a few timelines about how this technique was elaborated, the history of NIPICO. It all started in early 2015 when Christian Starnan was doing his PhD at Lund University under the supervision of Professor Rami Sankari. At that time, Christian developed a new ion time-of-flight spectrometer, and the main goal was to detect negative ion after photodissociation process. And at that time, there was, on reality, no Max 4. Max Lab at that time was shut down in order to go brighter, so it was still under construction. So what did Christian and his co-workers do? They went to Electra and they did commission the setup there, and they developed not only the negative time-of-flight spectrometer, but a complete setup called NIPICO to detect negative ion, positive ion. The negative part came from Max 4, and the positive part, or the positive spectrometer, was already available at Electra. And for some historical reasons, or because that PhD student, who is now also a colleague, was so proud with what he did. And this is normal, that when you do something, especially when you are a student, if you did it yourself, you feel proud about it. So he called the spectrometer Christian Toff, according to his name. And this collaboration between Max 4 and Electra during these years, between 2015 and 2018, successfully produced 6 publications. So there were at least 6 successful NIPICO experiments already published. And for historical memory, I would show the setup that was developed at Electra at that time. And I feel lucky that during these days, it happened that I visited Electra and I met Auntie there, but not Christian, and we did NIPICO experiment. But at that time, neither me nor Christian expected that this setup will bring me one day to Lund. So imagine the coincidence. Now I'm talking to you, and it amazes me, this coincidence, that this setup took Christian out of Lund University and out of Max 4. It was his passport to go to somewhere else. He got his PhD and he worked at Malmö University. And it was his reason to do beam times at Electra. So it moved Christian and his co-workers from Max 4 or from Max Lab to Electra. Now history repeats itself, but upside down. The experiment that took Christian out of Max 4 is the experiment that brought Hanan to Max 4. And vice versa, it's from Electra to Max 4 now. So this is one of the things that coincidence, you can feel it everywhere. It's not only the beat that you see in the spectrum. And back to the timeline, in 2019, Max 4 was already operational years before 2019, but at that year, FinEstBeAMS, which is Max 4 beamline that hosts gas phase in the station, was open to users. And the Christian TOF, which was originally constructed at Max 4, it was the time to send it back to his home. So it was sent back to Max 4. And then years after 2022, things went up a bit faster, and a new NIPICO setup was commissioned at Max 4 in collaboration between Auntie, Christian, and others. And in 2023, you know what happened. I came. Let's ask why FinEstBeAMS was the most suitable home for Max 4, for a NIPICO setup in Max 4. Simply because it's the only beam time that can host gas phase studies at the first ionization of any simple molecule. Knowing that the minimum energy available at this beam line can go down to 4.5 electron volt. This is reason, let's say scientifically point of view. Another reason, simply, it should be there because Auntie is there. Christian left Max 4, but there is still Auntie. So where should the setup go? It should be go back to its home, which is scientifically convenient, but also logically convenient, because there is a user. You can add a third reason, that one day there will be other users interested in NIPICO wishing to visit Max 4. So having the setup there would be a good reason. Now let's move to instrumentation. What does this NIPICO setup at FinEstBeAMS look like? This is a simple schematic diagram of the NIPICO setup. You can see that it's double time-of-flight spectrometers opposite to each other. One is dedicated for detecting positive ions, the other dedicated for detecting negative ions, or more precisely, for detecting negative particles. Negative particles could be ions, could be also electrons. And as you can see, we can divide this diagram into three regions. The first, to the region to my right, let's say the positive time-flight spectrometer, the other, the negative time-flight spectrometer, and in the middle is the interaction point. So the sample flows to the setup, and then light hits the molecule. The molecule fragments in any possible way. Positive charge, in order to find its way to the positive time-of-flight spectrometer, should be accelerated, and also negative charge. So in the region, exactly in the middle, there is a point of the interaction, and then there is a region of acceleration. So positive ion accelerated toward positive time-of-flight spectrometer, negative ion and electrons accelerated in the other way. But we are interested in doing NIPICO. We don't want to detect the electrons. So to get rid of the electrons, you can see there is a permanent magnet. Of course, it's here magnified. It could be small neodymium magnet. So there is a permanent magnet sit somewhere outside the vacuum chamber, just from outside, attached with some scotch tape. And this magnet would deflect the electrons, because electrons are much lighter than the negative ion fragments, so it will be sent away. It will be deflected away from the detection region of negative ions. But of course, you cannot deflect all electrons. Some will insist to stay. Those electrons could find their way to make some coincidences. That's why the spectrum is not easy to analyze. You would find other peaks, but it would be way cleaner, neater than the spectrum obtained for negative ions in conventional methods. This is, in this setup, using simple Newtonian kinematics, one can prove that the time of light, which means the time needed by the particle, positive or negative, to reach its final destination is proportional to the square root of its mass divided by charge. But in the experiment, we don't measure the time of light directly. We measure the difference of the time between the two detected particles. We take the start from the negative ion or negative particle and the stop from the positive ion. The difference between them is called the arrival time difference, which is the one that is produced during the experiment. This is a very simple simulation of the experiment. You see the photon will hit the molecule, and what happened to the molecule? It fragments. And this is an actual view of the setup after being assembled at FinEstBeAMS. Maybe it's clearer now after showing the schematic diagram. There is positive top, negative top, permanent magnet outside the chamber, and the sample and the beam of light. And this is a crowded picture. This is the real life. This is what you see at the end station of FinEstBeAMS when there is a beam time for NIPICO experiment. And talking about the instrumentation, we should talk about data. The experiment is so easy. Light hits molecule get annoyed, fragments, break apart, you detect the fragments, and that's it. No, that's not it. You need to do the data analysis. So out of the acquisition electronics, out of the software, I said we don't measure the time of light directly. Instead, we measure the arrival time difference, which is the stop time minus the start time. So it's the time needed by the positive ion minus the time needed by the negative ion to reach its final destination, which is the MCB detector. Once we get the arrival time difference, we collect the counts versus the time difference, and we obtain the NIPICO spectrum. On offline analysis, there is huge job to do offline, to do normalization, to find the yield, to integrate. So the intensity or the final yield will be the integration over the suitable arrival time difference range. And you get a typical spectrum like this one. In this spectrum, the two main components are the counts and the arrival time difference. The arrival time difference in NIPICO spectrum, contrary to the typical spectrum of BEBICO, which is photoion, photoelectron coincidence, the arrival time of difference is either positive or negative, could be zero. In the normal BEBICO experiment, it's always positive. But be careful, not all peaks in this positive, negative, zero range would be true coincidence. But the time could give you an information about what the peaks look like. So, as I said before, the time of light is proportional to the square root of mass over charge. Which means, if the time of light is, and its start, it's stop minus start. If it's negative, this means that the anion, which is the start, is heavier than the cation, which is the stop. But also, it means also, if it's the most negative value, it means it's the heaviest anion, the lightest cation. And the lightest positive ion to be detected would be proton, H+. So knowing two peaks in this spectrum is good enough to predict all possible or the time of all possible fragments. So the main challenge is to find two nicely intense peaks that we are sure about both the cation and the ion pair. did so, we can make the equation and we can predict the time of flight for each potential ion pair, or negative ion, positive ion pair. But again, one need to be careful, because there would be peaks, like for example, I took this typical spectrum from my data. If you look here, there are also nice peaks that are a bit small. I hope you can see them. Yeah, here. They are a bit small. We go back. This is the original spectrum. So these small peaks are true peaks. They come from negative electron, positive ion coincidence. They come from BLOCH. But they are not part of our experiment. So we should be careful about that. So some peaks would be deceiving. Always watch your peak, but watch with mind, not with eyes. Nice peak doesn't mean it's the proper peak. It could be something else. So always be careful when you watch your peak. And also, there are so many tricks that you can use to make sure that you are selecting the proper peak for your calibration. I mean, to get the equation of the time of flight. Among those tricks that you can play with the drift tube potential, so the proper peaks will move. Others will stay untouched. Or you can remove the magnet. If you remember the small magnet in the schematic diagram, you can remove the magnet. If you remove the magnet, all electrons will find their way to the detector. So the detector will welcome all electrons. So they will make coincidence with positive ions. So it will be the famous experiment of BLOCH. In that sense, you can also see that the BLOCH peaks will grow and the NIPICO peaks will diminish. So that's a trick also to find the proper coincidence peak. There is another thing that one should be careful about, the variation of the photon flux with the photon energy provided by the beamline. So this is the typical photon flux energy dependence of the finest beamline. So one should normalize the results before finding the total yield at certain photon energy of certain ion pair channel. What are the main characteristics of the NIPICO spectrum? The peak means coincidence, which means ion pair. The position of the peak means the arrival time difference, and the area under the peak means the count or the intensity or the portion of that ion pair channel production at this photon energy. And if we get these three information, the NIPICO spectrum is built, and the outcome is the arrival time difference spectrum versus different photon energy, which means that it's not enough to do that experiment for the single spectra that I showed. This should be repeated, and every time should be normalized, and each peak should be calculated for the arrival, for the proper normalized intensity. And at the end, if you did it for the full photon energy range, you will end up with your goal. You will find the appearance energy of the detected positive, negative ion pairs. And then you can talk about NIPICO results. Before I talk about NIPICO results, I would mention the NIPICO experiments that I have been involved in over the years, besides what I did in my visit to FinEstBeAMS. Mainly, I joined 4 experiments of NIPICO. The first one was at Electra in 2017. It was studying water molecule, of course in gaseous state, in the valence region. The other 3 were in MAX 4 during this visit, and propanol was done in the core region. As you can see, I put a cross on the third one, which is nicotinamide. It was the original proposal when I submitted the first proposal, and it was accepted, but it didn't work. And to be not biased, I will mention the 2 last experiments, one, let's say, sad story and one happy story. So let's start with nicotinamide. My proposal was to study pharmacologically important molecules, because you know our trouble in atomic and molecular field, that when you propose an experiment, they always ask you, what's the motivation, what's the application, how it would be useful for the humanity. Sometimes they don't appreciate that it's enough to be useful for the curiosity of a scientist. years after maybe the application could come. So I wanted to highlight that these molecules are applicable, they are important, pharmacologically important. Nicotinamide is important also for radiotherapy. Nicotinic acid is not only vitamin B, but also used for photovoltaic acid, so they are important. And what I added to that, they have been studied at electron in gas phase. So in gas phase, we evaporated these molecules. And even there was a third one, which is liquid, nicotine. So we did this study and we published the results, but we did electron spectroscopy. But I hoped that it would evaporate here, and I would do also NIPICO, because these molecules were not studied by NIPICO. But what happened? We sent the setup to the intensive care, because the sample, yes, evaporated, but contaminated the MCB, the microchannel plate of the positive detector, and we started collecting a few spectra, but then before the first night, we started to see that our detector needs to go to the hospital. So we decided to stop in order not to make the beamline manager angry, because I am, as a guest, I was relaxed. Normally when I go to the beam time, I'm not relaxed. I have 1 week, I have to finish my samples, I have to finish my experiment. But this time, I came as a guest researcher, and I have accepted the proposal. I was relaxed. But also, the beamline manager, if I put myself in his place, he's not thinking about this experiment. He's thinking about the next one, about the next user. So we decided to interrupt the experiment, and let's clean, let's open, let's bake the whole stuff. And this is what we did. And by the way, that was a sad story. But also we learned from that story. We learned that the current setup at FinEstBeAMS, it's good, important, unique, sensitive, but it's not convenient to evaporate powder samples. We should make an improvement for this point. So we learned something from that experiment. And we were brave enough to introduce a new experiment within the first night of the beam time, and we changed our mind. Let's do another sample. Let's do methanol. And we did methanol because we are sure it was not studied in NIPICO. There are a few studies in NIPICO, and most of them have been done by Antti, by Christian, by Robert from Elettra. So we know what have been done. Methanol was only done in core region. It was not done in valence. And I proposed to do nicotinamide in valence region. So methanol was a good replacement to save the time available of the beam time. Other reasons for doing methanol, its simple structure. And its simple structure means it would be a good candidate to expand our future experiment to study more complicated molecules, especially more complicated alcohols, because all alcohol molecules are important. So it would be nice to study them using NIPICO. Another reason that its simple structure makes it potentially producing negative ions. So we think from its structure, CH3OH, most likely it will produce some negative ions, so it will be good candidate. And above all, it's volatile at room temperature. So it can evaporate safely, smoothly, without risking the detector, without being stressed. And that was successful, and I will show you the results. Here are the results of valence, photon, what happened? We are there. Here are the results of valence photon excited methanol. This is one of the typical spectra of photon excited methanol detected by NIPICO technique. This was done at 13.8 electron volt. You can see there are 3 ion pairs detectable at this energy, at this photon energy, and you can also see that they are nicely sharp, and the spectrum is very clean, very neat. I have to tell you that this was collected in more than 12 hours. So this single spectrum took more than 12 hours. And this spectrum means a point in the spectrum of the appearance of the total ion, of the ion yield of the certain ion pair. So it's a point for each certain ion pair. So imagine how much time it needs. And this was repeated for full energy range of our interest. We started from 11.2 to 13.4, and we at that range we noticed that at the very low energy, about 11 electron volt, there was no noticeable NIPICO peak. But we went higher in photon energy. We started to see 2 ion pairs. So this encouraged us to go further higher, up to 16.4 and then up to 30. And you see here that the other ion pair started to show up. After normalizing these spectrum, as I explained in the NIPICO characteristics, we obtained, or we ended up with the intensity or the count of each ion pair versus the photon energy. And this is the most important outcome that enable us to say at which photon energy this negative ion would appear or this ion pair would show up. If you look at the spectrum, you see that it's kind of mismatching because it was done using different energy ranges and it has been normalized. And again, I re-emphasize that each single point in this spectrum means hours of data acquisition from other single spectra. So each NIPICO spectrum will end up as a point in this spectrum. And on the top of this spectrum, I could show the total ion yield, which was also recorded within the experiment. To summarize these results, I would say that we have detected 5 ion pairs in this experiment by valence exciting methanol at the selected photon energy of our study. But most important to highlight that NIPICO technique at finest beam proved to be feasible for the valence photodissociation studies. So if it was successful for methanol, it should be successful for similar simple molecules and hopefully for more complicated molecules. And looking toward the future, it's not a secret that we have submitted another proposal and to methanol sister, which is ethanol, and it's exciting that it would accept it, but I should keep calm before becoming super excited because fund has not been secured yet. But at least I'm happy for getting it accepted because this means I will be back. Sooner or later, who knows? And by this, I'm almost done, but there are a few spectra, few further insights I would like to share with you. You may like them, you may not, but I feel not satisfied if I didn't say them. In order to show further insights, let's show you other NIPICO spectra, not those spectra that have been collected for overnight data acquisition. I will show you other kind of spectra. Let me start with this one, which summarizes years of atomic and molecular physics work. It's my photo with the old NIPICO setup, the inclined setup at gas phase beamline in Electra in 2017. And to the right, it's my photo with the new NIPICO setup, the flat one, in Max 4. I think this photo summarizes how coincidence played a role, at least in my own life. And when I look at it, when I took the photo months ago at finest beam, I didn't remember that my photo with the NIPICO setup would be using the same color of dress. And I said to myself, oh my God, it's really, truly coincidence. Another spectrum, I would show this one. In this one, you can see 4 peaks in the spectrum. Those are the people that were working on NIPICO, part of the people that were working on NIPICO at the gas phase beamline at Electra. And you can see the highest peak is Antti, no surprise, because he's here, the manager of the NIPICO setup. And this photo is dear to my heart because now I felt that, oh, it was worthy to join it in 2017. And the last one, this is the dearest to my heart. This Max 4 Electra selfie. You should call it Max 4 Electra coincidence. So the good experiment is not the experiment that ends up with data. The good experiment is that experiment that combined people laboratories from different countries to show up in the same experiment, at least in my own point of view. And as I said, in my own point of view, I wish to show you what NIPICO, or how is it seen through my eyes. Maybe, is it data to analyze? Is it night shift to live with? Is it Electra Max 4 coincidence or Electra Max 4 link? Is it my visa to come to Lund? Is it to work again with someone so organized and so dedicated to his job like Antti? Is it all? Actually, it is simply coincidence. All these together come into coincidence when I think about NIPICO. But, as I said, it's simply coincidence. I can tell you that coincidence, in its meaning in physics, not as it is meant by literature. In physics, coincidence has different meaning, as we know it in the spectroscopy. But in literature, it means by chance meaning. So coincidence played a remarkable role in my life of physics, in my career, let's say. And I can simply say it marked all my good beginnings. How? The first coincidence challenge in my life was the biggest challenge. In 2005, it was the year that I entered the University of Jordan Van de Graaff Accelerator. It's an IMBM accelerator called JOVA. It's the place where I was born as a scientist. So in that year, I started my PhD experiment. And I still remember when I met my two advisors at that time to propose an experiment. One of them introduced me to the terminology coincidence, and he said, why not you develop a new technique, it was really a new technique at that time, called coincident Rutherford backscattering spectrometry. Normally, Rutherford backscattering spectrometry is an beam analysis done for thin films and solid tablets. I did it for gaseous, and I did it in coincidence. So I was supposed to do this, CRBS, coincident RBS. I can tell you, it's a story that I would like to live, and I rarely do to tell. I will tell you, at that moment, I took a stop and I was about to say no. Because to me, it was the first time I hear this word in physics. What does it mean, coincidence? Now you may think that I was a weak PhD student. No, I was a fresh PhD student, and I can tell you, I started my PhD directly from bachelor. I didn't have master. So my PhD experiment was my first experiment in life. And my PhD advisor was my first mentor in research. So it was my first research. So when I heard about coincidence, I got shocked. What does this man say? Does he say that I should work and something happens incidentally? How it comes with physics? And I was so passionate about physics, so passionate about atomic and molecular physics, and I know how much time is precise in life and in atomic processes. So I was shocked. What does this man say? And I was about to say no, I will not do coincident Rutherford backscattering spectrometry. But I took a breath and I tried to calm myself, and I said, look, this professor is known in his field, and he's the only one working at JOVA. If I say no, I will lose my dream. I will not work in an accelerator again. So I should be patient, I should read. And when I read, yeah, it was related to physics. It doesn't mean anything related to by chance, not planned, unintentionally. It means intention. It means plan. It means within a certain time difference. It doesn't mean by chance. It doesn't mean incident. So at that moment, I started my PhD work. I started my PhD experiment. And I can tell you, it was the biggest challenging coincidence experiment in my life up to date, because it was very long night shifts. And I was alone. I was the only PhD student working on that experiment. It's my own experiment. I have two advisors, but none of them did any night shift. It's my job, it's my duty, it's my experiment, it's my PhD degree. So I spent years in that coincidence measurements. And to me, at that time, I learned the wrong lesson. I learned that coincidence means not only low count rate and long night shifts. It means that I have to give all my life to the coincidence measurements. I should keep watching my beaks. My beaks, the most important thing in my PhD degree. I should take care of my beaks. I should give my life to the beam time. If I have beam time, everything else should stop. I should overcome challenges. I should show resilience. It's good to show resilience. It's good to live a challenging life and to overcome challenges. But at the end, it meant also to me, if I do coincidence experiment, it's in a way or another means loneliness. It means that I do everything by my own, that I am alone. And to be honest, that was, for me, it was fine. I loved my work. I loved physics. And I sustained, and I got my PhD, and up to date, I'm proud of what I did. But also it meant an angry mother. My mother was not very happy during the experiment. But I was smart. I was always telling her, look, tomorrow I will finish my PhD. This is the longest experiment in my life. I was right. It was the longest experiment, but it was not the only coincidence experiment. So my mother believed me, and she thought that after I did my PhD, after the defense, I will live a rosy life. No coincidence anymore. I will be the professor that I showed at the beginning, and my life would be quite easy, at least without the physics coincidence or the physical coincidence. But it's the only promise that I didn't meet to my mother, because years after, I had the chance, thanks to ICTP, to go to Electra. And since 2015, up to date, I am collaborating with Electra. And as I said, coincidence marked many important beginnings in my life. My first experiment at Electra, what was? It was BLOCH. It was again coincidence. And for my mother, it means I am out of life. But that didn't happen because I found myself in this atmosphere. I was not anymore alone. Coincidence means low count rate, long night shift, challenging spectra, dedicated beam time, but it doesn't mean that you do alone. It was the wrong lesson that I learned years ago. So I changed my mind. Coincidence is not that hard. Coincidence is all what is good about collaboration, about cooperation, about team working, about meeting people, about traveling also. So many things are related to this kind of measurements. And if you want to squeeze all these words, it's simply collaboration. Go coincidence doesn't mean go alone, it means go together. It means collaborate. And for that, the best ending of these insights would be the acknowledgement, starting with the gentleman who invited me to give this talk. He was hunting for a speaker, and I don't know how he caught me among the all esteemed staff in this facility, but I would say I'm thankful for that. And again, I thank my colleagues, Auntie Christy and Kevin, Richard, for their contribution for the data presented in this talk. And also thanks to the white hands of the FinEstBeAMS guys who helped me during, before, and after the experiment. And also, this visit was fully funded by the Swedish Institute through an agreement for an exchange scholarship between Sesame and Maxford, and governed or under the umbrella of Lund University. And saying that, I cannot forget to thank the nice people who make this scholarship useful for me, starting from Professor Sperker-Wirren, who was the person who believed that postponing the fellowship or the scholarship doesn't mean deleting it. So I got it accepted in 2020, and I used it in 2023 because of his kind endorsement. And of course, I thank Alexandra and Miss Suzanne the receptionist, and Alexandra, the financial officer, not because of doing their job. I know they did their job, but because they did their job with a nice smile. I can tell you that working in Maxford is very nice, but without meeting a receptionist like Miss Suzanne, it would be somehow different. And also the same goes for Alexandra. And Khadija from BLOCH Beam Time, she was a good friend, and she was a perfect photographer. Many of the photos that you have seen with Max 4 have been collected by Khadija, and needless to say, huge thanks should go to Auntie. I know my visit before I arrived and now and until I leave made you busier, and you are already busy, but made you busier, but at least I hope it also made you happier. And to the whole environment, if I forgot anyone in Max 4, I would like to say I enjoyed my visit here since the last moment, since the 0 day. And normally, I don't agree with directors, but it happened by coincidence that this time I admit that I agree with your director when he said in the previous staff meeting about working here, it's all what you want from a job. That's definitely true. And it goes without saying, I'm grateful to ICTB, my gate to Europe, my gate to the world, and also to Electra. It's the place where I developed all my expertise in synchrotron radiation, and without working with these nice people, you would not see me standing in front of you, talking to you today. And last but most important, I'm grateful to my university for granting me a teaching free leave for 2 years in a row up to now. And that's almost all. But if you're ready to hear more insight, someone said at the beginning that it's my day. Who said? Someone said it's your day, take your time. I said, yes, it is my day. Actually, it's not my day, it's my month, May, because I was born like 2 days ago was my birthday. So these days, my mother is celebrating 43 years of my life. And I personally celebrate 18 years of working at an accelerator. So it's special in my life. 2 days ago, a good friend here brought me some Italian chocolate to my desktop. I was so busy with doing the presentation, I forgot for a moment that it's my birthday. Who knows that in Max 4? Nobody. And when I found Italian chocolate on my desk, I started to think, one should think about the history of his life. One should take a moment of some meditation to think what happened during these years. And because I was working on this presentation, I started to think of my 18 years old in an accelerator. You see how ladies can make themselves younger? Count your work years. And then I would like to say I always believed, since I was a student, that the best place to do physics and to enjoy experimental physics and to attach people to physics is to work in an accelerator. But also, as atomic and molecular physicists, I do believe that we enjoy doing experiments for so many reasons and in so many ways. And many of these reasons and ways, the good ones of them, come in spectroscopy. And also, many of these reasons come in coincidence. And I think you agree with me that life is too short. Life of everybody is too short. So if you are going to live one life, don't waste it in doing silly things. Invest your life by doing good things. One of these good things, one of the best things to do is to work in an accelerator. And if you get bored one day, why not to go to a new accelerator? Try to explore new accelerators. And here I am quoting the words that have been said with my colleague, Kevin Prince from Electra, who's actually more than a colleague. He's a source of inspiration to me. He was the first to host me to a synchrotron accelerator or synchrotron light source. Months ago, when he came here to the beam time of NIPICO, at the last night of the beam time, before he said goodbye for me and Auntie, he said, I am wondering why people go to islands and spend money to go to museums and so to have fun. Why shouldn't they go to accelerators? Why shouldn't they go to synchrotrons? And I second on what Kevin said, but I add, that's true, but 2 synchrotron light sources would be better than 1. And also, if you are lucky and have the chance to work in other synchrotrons, many accelerators would be better than 2. That's all. I would be happy to get your questions if you have, and if you like, the Palestinian cookies are waiting for you for the probably my last FICA in Max 4. That's all. Thank you so much. Thank you, Max.